Okay. So, good morning to everyone. So, welcome to this session, 5th day, first session, which is hands on C2000 DSP microcontroller. So, this we included this microcontroller session in this course, so that we can give you some overview on C2000 microcontroller, and you can do some basic programming, and also my student will explain you how it can be done for how it becomes further useful for power electronic converters. Now, as I explained in my previous session that power converter is the power converter is there, but the brain of the power converter is the control, which can be implemented using any controller. So, there are controllers like FPGA, Arduino, and then DSP microcontroller. This DSP microcontroller is one of the most stable microcontroller that we use for power electronic application. So, in this presentation, we will start with the overview of TMS 320F2839D microcontroller, DSP microcontroller from Texas Instruments. About its launchpad, pin overview and description we will explain. So, how it can be interfaced with MATLAB, how you can. So, there are two ways. One way is you install CCS, Code Composer Studio, in your system, and then you do coding, and then accordingly there are modules available in DSP microcontroller that you can use to generate the PWM pulses, and also you can use the ADCs to for closed loop control. So, another way is use MATLAB interfacing. Using MATLAB, how you can utilize this programming of this microcontroller. Now, GPIO module, EPWM module we will explain, DAC and ADC module we will explain in this session. Now, this is the C2000 microcontroller unit, where we have sensing, processing, interfacing and control. Okay. So, this is actually this is FPGA is a little bit on it's costly, little bit costly, and if you see Arduino is the processing speed is slow. So, it is we feel like that DSP C2000 microcontroller is an optimal solution cost wise and speed wise, and it is you can implement this power electronic control easily. So, what we have here is, for processing we have floating point DSP C2000 C28X core and parallel multi-core architecture, and then interfacing we have CAN and other facilities, communication facilities are there, and then in control we have high resolution PWM we can generate. We have EPWM modules that also we will explain in this session, and then we have sensing, where we have 12 to 16 bit ADCs are there. Okay. So, this makes this a versatile microcontroller for power electronic interfacing. So, from now onwards my PhD student Alu Bhargav will explain you, and he will demonstrate how you can interface this C2000 microcontroller with MATLAB, and the PWM pulses can be generated. So, over to you.
Now we are going to see how to interface the TMS 320F28370 microcontroller, how to interface with MATLAB, and we see how to interface that few modules, and we see the results on the DSO. Basically this is the board TMS 320F28370 launchpad. we are going to do few analysis, few demonstrations on this, how to interface and all. And in this module, we have GPIO modules, we have ADC module, DAC module, and we have communication interfaces like SPI, CAN, and UART also. And it is interface to USB. This is the XTS version 200 version 2, which you can interface from USB connection from MATLAB. And now let's see what are the features of TMS-28370 controller. It has clock frequency of 200 MHz, and it is a 32-bit processor, and it has a trigonometric math unit CPU performance, where we can perform the trigonometric expression functions also. And it has a programmable control law accelerator, where we can accelerate our accelerate our functions and all. And it has a on-chip memory of 512 KB and flash memory of 1 MB. And it coming to here, and coming to EPWMs, here we can see there are 24 PWM modules. Among them, we can which are used for high frequency purpose to generate high switching frequency. And among them, if you want to go very high switching frequency above 100 kHz, there are 12 HR PWM, high resolution pulse width modulation pins are there, where we can achieve more than 100 kHz also. And there is a support of deadband calculation, deadband support also we can have here. And we have here 6 capture modules. We can capture different events. And we have here encoded pulse modulators, where we can capture the rotary motion, where we can interface our machines. We can achieve the machine model. Now coming to ADC channels, here we have different type of ADC channels, and here we have 4 ADC converters, in which there is subsystem. There is every module we have again 4 ADCs. So total 16 ADCs we can have in the module. And here it is one sampling and hold circuit for ADCs for every one module. Now coming to ADC channel, here we have 16-bit channel and 12-bit channel also. So we can achieve in 16-bit we can achieve 1.1 mega samples per second, and in case of 12-bit module we can achieve 3.5 mega samples per second. And here are DAC channels also. Here in DAC channel we have 3 DAC channels, which is a very advantage compared to other families of C2000. In this module we have 3 DAC channels. We can see our results on DSO, and we have here communication peripherals. We have 2 CAN modules and 3 SPI ports and 1 USB debugging and 4 serial communication interfaces and 2 I2C. And here you can see that this is the overview of our board. Here you can see this J14, J15, J12 are the quadrature encoder module and CAN module, and you can see J13 and J11 will be I2C module, where you can interface, and J5, J7, J6, J8 and J2, J4, J1, J3 consist of ADC modules and pulse width modulation pins. And J21 is the ADC differential input. J21 will be the, again you can see here J2 and JP2 and JP1 is having power supply, where this disables the isolation from ground. This disables the ground from our CPU and the board. If you remove the pins, then we can achieve all the isolation also. And this is the pin overview of our launchpad, which can you can see that on right side we can see on right side of here you can see that there are PWMs from 1A, 1B, 2A, 2B, 3A, 3B and 4A, 4B. Total 12 PWM pins are available here. And in the left side you can see that we have almost 16 ADC pins. And among this among 16 ADC pins, we have we are using 2 ADC pins as a DAC also. And this is the overview of the chart diagram. Now, why we want to interface our MATLAB coding compared to CCS? So you go writing the code and landing a code and writing a code will be a tedious task. So to remove that tedious task, the MATLAB has introduced this feature to which generates automatically the code by generating from the blocks itself. So to generate the blocks, we need to interface our C2000 board and MATLAB. So we see how to interface it. So I am opening a laptop MATLAB 2020. We are using MATLAB 2023A. So first of all, we have to go to on add-ons. And here we have to search for C2000. And we have to install this C2000 microcontroller box set, which is in which our laptop is already pre-installed. We have to install this C2000 micro block set. After installing this, we have to go to Simulink. Open blank model. And here we can see now we have already installed our MATLAB, installed our C2000 micro block set. So we have to see here, we can see in the library browser where it is installed on. You can see here we have C2000 microcontroller block set. You can see here C2000 microcontroller block set. They have different families of C2000 microcontroller. So among them we are choosing our F28379D. There are different families, so we need to interface F28379D. So we need to check whether the family has been installed or not. See, we have different family here: ADC, CLA subsystem, and DAC, digital input, digital output, and we have EPWM, QEP, I2C. We have different type of modules here. So now we need to interface our MATLAB with C2000. So go to modeling, model settings. Then we have to go to hardware implementation. Then we have to select our board. See, here we have different type of boards here. We have different Delfino, Piccolo boards and all. So we are using now here you can see here there are two types of 28379D launch pads. One is TI Delfino 2837XD and TI Delfino F28379D launch pad. So if you are using chip type, then we have to choose 2837XD, and if you are using launch pad, then we have to select specifically launch pad. So I'm selecting the launch pad, and MATLAB initializes hardware parameters automatically. And see, after getting this, after getting a device vendor Texas Instrument and device step, then we have to apply it. Then OK. Now we have set up the we need to we have connected the hardware part. And this is the board which we are using now, and I am connecting the board now. Then go to here hardware settings. So we have to set up the hardware. So here we can see here select another hardware board, set up hardware board and all. So we have to set up the hardware first of all. So I am setting the hardware. Here we get different type of multiple processor families, and we have to select which family we are going to use. So I am here using 28379XT. So I am selecting the 28379XT and going for next. And we have to install these third-party software apps, and we have to install them. They are already installed here. So I am going further. and we have to install these third party softwares, and we have to install Control Suite, CCS and C2000 software, and we have to take care while installing them, because if you go for higher version of MATLAB, the version may change. So we have to see which version of CCS and which version of C2000 we have to select, and this is the version they will be giving here, and we have to validate the path. After validation successful, we will get a summary of the third party installation, and it's done. So our board has been interfaced with the MATLAB. So now we have to see how to let's have a how to generate pulse width. Let's see the output, whether the board has interface or not. So we'll go for generate a small pulse generator, and we'll go for general purpose input and output pin, where we can see the general purpose input and output pin can be utilized either as an input or output. So right now here I am giving pulse generator, and I am using the GPIO pin as a output pin. So I am generating here pulse generator, and I am giving 1 amplitude, and I am giving 2 kilohertz and 50% duty cycle. Now I need the GPIO pin. So we need to go to library. So here we have GPIO pin in digital input and digital output. So we need digital output. So I am taking to digital output. So I am here again. We are having GPIO pins. You can see here we have multiple GPIO pins. We have almost 119 GPIO pins here. So we need to select one GPIO pin. I am selecting. If you go for this GPIO pin, with GPIO pin I am selecting 0. So GPIO 0 will be like see, you can see here in the left side bottom picture mein, we have in pin for J4 40 pin. You can see here GPIO 0 is interfaced with 40 pin. So we have to after generating the code, we have to check the pin pulse at 40. So I am selecting it for GPIO 0. I am applying it. Then I am building the program. So here you can see the process of programming. The MATLAB itself generates the code and process it and install the CCS, and it will it debugs in the microcontroller itself. We just have to see the output at 40 pin. You can see here the process has been done, everything. So MATLAB has processed everything, and finally you have to get load and run and done. That means that your program has been executed in the microcontroller. Now we have to check in the see here we are getting this pulse width modulator. here we can see now the pulse width modulator has been generated with pulse width of 50%. We can see here 50% duty cycle, and we can see here frequency also 2 kHz. As we are given 2 kHz, we are getting 2 kHz and 50% duty cycle also here. As we can generate pulses from GPIO pin, why we need to go to EPWM. See, there is a limitation for GPIO pins also. There may be chances of missing the pulse at high switching frequency. So we require precise pulses. So we go for EPWMs. So I am keeping now in EPWM. See, we have EPWM here. Then how to generate the pulses from EPWM? We cannot give directly pulse to the pulse generator to the EPWM. So here you can see that how to the pulse width mode EPWM will have it can build itself a triangle or a SATU generator. We have to generate from the block itself. So here you can see here we have EPWM. We have multiple events here. So we can we have multiple options here. So we'll let me explain. So EPWM pins, you can see here we have 8. It's a 16-bit time-based counter, and it has 8 sub-modules. One is clock prescaler, and from there then we can go for counter compare, action qualifier, deadband generator, PWM chopper module, trip zone, digital compare, and event trigger. From EPWM, from PWM module, you can trigger the event also. We can stop the event and we can trigger the event also. Then what is this time-based counter compare? And most commonly utilized by EPWM modules are time-based counter compare, and action qualifier, and deadband generator. Why this time-based counter? This time-based counter is utilized for generation of sawtooth and triangle generator, and counter compare, it compared with triangle with the duty cycle which is given from outside. Then action qualifier module is utilized to take what action at what event, and deadband generator will generate deadband between 2 pulses. Now this is the then how to generate this sawtooth generator or triangle generator. So the sawtooth generator will not be a ramp in our C2 microcontroller. It will be in steps of in terms of counter, and that counter will be decided and the counter will be decided by the clock frequency, and the clock frequency will be set by us. So you can see here I am trying to generate a sawtooth generator in terms of counter. See, counter is going from 0, 1, 2, 3, 4, and after 4 I am setting it to 0 again. So my counter is here 4. Then so counter itself is also called TBPRD, or it can be called as TBCTR. It can be done, and TB clock is the how much time that the counter should be in the state, and after which state after that particular time the counter should increment. So that is the TB clock. So if you now from this you can say that, see here TB clock, the time period taken by TB clock, and from here TB clock into a counter. Then why this 1? Because we are counting from 0, so we have to add the 0 also. So the counter, the TBPRD will be 4 plus 1 will be total 5, and into the clock, the time taken by the each counter will be our switching frequency. And similarly, in case of triangle generator, we can see here it will be TPWM will be two times. It will be 2 times TBPRD into T clock. And see, this is the this is how a sawtooth generator will be generated in C2 microcontroller. And I have shown you that here TBPRD we can know how many steps. Then how to decide this TB clock. So TB clock will be decided from the system itself, or we can give here. We have to prescale it based on the TB clock. So first of all, the TB clock will be 1 by EPWM clock by HSP clock and clock division. So HSP clock and clock division will be a pre-scalar. We can reduce the clock frequency or we can increase the clock frequency based on our feasibility. So first of all, for 1 by EPW clock, this EPW clock is equal to system clock by 2. So system clock will be the clock frequency of our microcontroller. So in this board we have system clock frequency will be 200 megahertz. And you can see in the right side there is a clock division. You can see here, if you give 1, then it will be divided by 1. If you give by 2, it will be divided by 2. Then we have to go 4. Similarly, we have to give in terms of values. Now coming to action qualifier. In action qualifier, we will decide how to what actions will happen at what event. So here in microcontroller board we are having already a predefined register for that, where the actions will be stored. And here you can see now I have generated a sawtooth triangle. See here I have already generated a sawtooth generator by deciding the TV clock and TV PRD. Now at what event? Now say the compare A is our, let's say my compare A is our duty cycle duty A. So from duty A it is meeting at, so what happens at when our triangle is 0 point, what actions will be done? That I am deciding here at when compare A is equal to 0, when this at 0 it has to be set. So I am setting it up, and when throughout the time there will be after when compare A meets our duty cycle, when duty cycle meets our sawtooth generator, at that time I am setting the event such a way that it should clear it. Whatever the set option is there given, it has to clear. So what happened here? Now the option has been cleared. So at 0 it has been set, and when compare A is met with our triangle generator, sawtooth generator, that it has been clear. Again at period there will be no action. I am not doing any action here, but again here what happened? Again the 0 has been come here. So at this 0 again my action will be set. Similarly for compare B also. In compare A, I am when compare A is equal to 0, then we can say that there is a set, and when compare A meets out the sawtooth generator, then this is the action where CBX is written. There we have to clear out. Similarly, in case of triangle, here we have up counter and we have down counter also. Similarly, here we have, this is up counter, here we have up counter and down counter. So we decide here events like 2 times. One during up counter what actions will be done, and during down counter what actions will be done. So I am saying now here I am setting in such a way that during up counter, when our triangle generator meets our CMPA, then the action should be the action is set, and during the period time there will be no action here. And during down counter, what happened? I am setting in such a way that when triangle generator meets the compare A, it should be clear. Similarly, in case of compare B, when during up counter, during the period it should be no actions will be done, and during when compare A meets our triangle generator, it should be set, and during down counter it should be clear. Let's have a small example here. Now here I am saying I have already switching frequency of 10 kilohertz. Now how to calculate that TBPRD value and TB clock value and all. So here you can see that TBPRD equal to TBPRD. See, I am saying only here up counter, not up counter, only up counter. So in up counter the formula is TPWM equal to TBPRD plus 1 into TB clock. So in TBPWM will be 10 power minus 4, and I already previously defined that EPWM clock will be system clock by 2. So system clock is our 200 megahertz. So 200 by 2 equal to 110 power 6, and now I will calculate TB clock now. From TB clock I can get it 1 by EPWM clock by HFC clock and clock division. And this SFC clock and clock divisions are pre-scalars. So I am defining it as 1 1 now. For timing I am taking it 1 1 and I am calculating the TB clock. So it will be 10 power minus 8. Now from that I can get TBPRD equal to TPWM by TB clock minus 1 equal to 999. So my now TBPRD is 4 nines. So let's see this 10 kilohertz frequency from in MATLAB. See here, here this is the timer period TBPRD. As from our calculations, I am getting 499. So I am setting up here, and I have defined that there should be up counter only. So we have different counting modes here: up counter, down counter, up down counter. So we are calculating up counter, and see again here. This is the pre-scale dividers where TB clock, so this is TB clock pre-scale divider, which can be HSP clock division. So these will be 1 1. See here we have 1, 2, 4, 8, 16, 34. So based on that I am giving only 1. So I am taking it 1 1. Now I have to give the counter compared. So CMPA, CMPAB. So I am giving it out from, there are two types. We can give the value here, or we can take from input port. So I am taking from input port. And you can see here we have deadband also. We can use deadband modules. The deadband will be explained later. And now action qualifier. What action I should take? As I said that when counter equal to 0, it should be set. So I am setting it up. When counter equal to period, it should do nothing. And when counter equal to compare A, it should clear. So in case of B, it should be nothing. So we have got here the output. Here we can see that we have get access for our compare A. So I am giving constant. See inside we have given. Now what happened? The compare A has to suppose this is 4 nines. So now our comparing generally our duty ratio will be 0 to 1 only. So to match this value, to match this value, we have to add a gain in such a way. This will be in terms of 10,000. This will be like 99 TBPRD plus 1. We have to add the gain in such a way that will be TBPRD plus 1. So I am adding a gain here. Sorry, it's 10,000. I am giving duty cycle of 0.5. So now I am generating a 0.5 duty cycle with 10 kHz and 50% duty cycle. So I am building it up, and here see I am given a EPW. We have different GPU modules, but I am choosing EPWMA. From that from presentation we can see that EPWM1 will be 40 pin. It is interlinked with GPIO 0 and EPWM1A. So we can see the output at EPWM1A. Sorry, I have to delete this. The other was because of I have used the GPIO pin and EPWM single time, so you should not use that one. So see we have generated, see here, check here, load, run and done is done, and you can see here 50% duty cycle has been achieved and the switching frequency is 10 kHz. So whatever we expected we have achieved from the EPWM pin. Similarly here you can see that if you want, now I am using here EPWM1. If you want to use 1B also, we can use here EPWM-B and enable it and set the actions, and then if you want and we can give here similarly compare A here given from input A. In similar way you can give compare B also from input port B, and you can give from input port B, and if you want the deadband also we can use EPWM deadband for both of them. So deadband, how here we have different type of deadband polarities here. So active high, active low complementary, active high complementary, active low complementary. What are these deadband complementaries? You see here in presentation. So why we require this deadband? When we give this deadband, in case of inverter modules, we have two switches which we have to two switches will be one lag. So if there is no gap between two pulses, there may be chances of turning on and turning off time will be same of the two switches, and due to that there may be a short circuit of the DC bus. So that will be an failure of our power and converter. To avoid that, we need deadband between two switches of the same leg. So as I said, there we can see that there are four different type of deadband polarities. We can see here active high complementary, active low complementary, active high and active low. Suppose this is in active high complementary. You can see here we have based on this diagram we can set which is our suitable deadband we require. In case of inverter, let's have first of all active low. So when the switch is turning off, the other switch will be also turned off with having a gap of raising a delay and falling a delay. So this is not what we require. One switch will be turned on and one switch will be turned off. So this is not this is not what we require in inverter. So then go for active high. In case of active high, see this is the signal which EPWM-A is turned on. So during turn on, the EPWM-B is also turning on. So this is not which we require in inverter. Now coming to active low complementary. In active low complementary, when switch is turned off, this is the EPWM-B will be turned on. But here what happened, there is when EPWM-A is turned on, EPWM-B is also turning on, which makes a short circuit condition and damage of DC bus. So this is also not which is required. So we have then go into active high complementary. In active high complementary, you can see here when switch is turned on, there is a turn off position of. So before the switch is turned on, the EPWM-B is turning off. So that means that there will be no chance of short circuit at any case. So we use for inverter active high complementary. Similarly, as per requirement, you have to decide which deadband polarity you require it. So here I am choosing active active high complementary, and here you can see here I am giving different value for raising edge delay and falling edge delay. For raising edge delay 100, I am giving 100 equal to 1 microsecond. So if you give 100, then delay will be 1 microsecond between raising edge and falling edge. And in case of B, I am setting it set, and period it should be do nothing. Sorry, it should be opposite. So you can see here I got access of EPWM-B also. Similarly, I want EPWM-A, EPWM-B in case of by using only one duty cycle. So that can be done without enabling the EPWM-B. Automatically, if you enable this deadband, automatically the active high complementary will come to EPWM-A and B. So you can see here. Here I am connecting another channel also to see the deadband and two different EPWM-A and B in one channel, 1A, 1B. 1A is at 40 and 1B will be at 39. See here you can see this, I am setting as each time block has 5 microseconds, and you can see here so now I set as, you can see here to EPWM-A and EPWM-B, and you can see here we are having a gap of 1 microsecond. I have set a block such that one division will be 1 microsecond, and you can see here we have two pulse width modulation have been generated which is complementary to each other, and we have a gap of 1 microsecond between them. So 100 equal to 1 microsecond. So if you go for 200, 2 microsecond, 300, 3 microsecond. So you can see here at falling edge, at rising edge we have one gap like wood delay, and falling edges we have another delay. Now we see how to use the DAC. Now you can see here DAC. We need to see the sine wave from the DAC. We can see the sine wave from the DAC also. But why I have added here? I have added here 1 to the sine wave, because the DAC TMS microcontrollers will not take any negative value. We have to take to positive value only. We have to give everything to positive only, and then we have to add a DC offset, and then after getting our signal out, we can reduce, we can make different subtract it -1, and we can get our own signal. So here I am adding it sine wave, here sine wave, and then I am adding 1 to it, so that amplitude is 1 to -1. He has been shifted to 2 to 0 now. Now my sine signal will be from 2 to 0. So I am saying sine. So I am using this amplitude 1 only, and I am using frequency 2 into 5. It's in the radians, so I have to give in 50, and then I am giving sampling time as 5 e power -5. So I am adding constant. I am taking here from DAC. So here we are converting the digital to analog, right? So the whatever waveform we have to give in digital waveform, but we are giving, this is completely analog waveform, and this is asking digital waveform. So to convert that analog to digital, we have to add the gain of so we need to add the gain such a way that this is the gain which value will be like, is a 12-bit DAC converter. So we have to use 2 power 12 minus 1 equal to 4095, and we are giving a signal with we are giving the V reference will be 3. For this board V reference is 3, so we are using this as the gain value. This is the gain value for this gain. So our analog syllable will be converting from analog to digital for the DAC converter. In that block, you can see here we have three different blocks A, B, C. I am choosing here A. So that the DAC A pin block is 30. Pin number 30. We can see DAC A. We can see output of DAC A. So I am building it up. See, you can see whatever we have generated a sine waveform in the MATLAB, we can see from DAC here. So, and you can see here waveform is having, you can see here amplitude is 2 volt and 50 Hz frequency. We have given why it is amplitude 2, because we have shifted from negative to positive everything. So, plus 1 to minus 1 to it has gone to 1 and 1 will be 2, and maximum will be 2 and minimum will be 0, and it is getting 50 Hz frequency. We have generated 50 Hz frequency. So, we got the 50 Hz frequency, and maximum value is 2 and minimum value is 0. Similarly, we can see other outputs when we perform any control algorithm. We can see our duty cycle in the from DAC, or any parameter we want to check. We can check from DAC. So, DAC will be very useful for us when performing any experiment or any control anything analysis we are doing. Now, last will be like ADC converter. Say here we do not have any physical analog, we do not have any physical practical scenario of the analog signal from outside. So, to read the ADC, I am giving directly from DAC what we are reading from DAC value. We can give this as a ADC pin also. So, I am using DAC A as the analog input to my ADC. So, here you can see ADC block. Here we say there are multiple modules. As I said, there are 4 different modules in TMS-228 to 370. There are 4 different channels. So, A, B, C, D. Each channel will have one ADC converter. So, from this is I am using here 12 bit. We have access of 12 bit and 16 bit. I am using here 12 bit 12 bit, and the starter I am using this is SOC. These are the SOC numbers where our starter conversion of ADC should start. So, I am giving this trigger number as 0. And in software trigger source, we have software, we have CPU timers, 3 different timers, software, and we can trigger from EPWM. As I said in EPWM, I said that you can trigger the event from EPWM also. So, there are multiple triggering events, but for here I am using software, and sampling time I am giving 5e power 05, and I am using A module. So, in A module, which pin I have to take it? So, that pin I will decide from here. I am taking here ADC into, because this pin is nearby to DAC. So, I can to have the access I am using ADC into. People can take ADC 1 to 4, 1 to 3, any pin can be utilized. So, I am taking this J. I am using this jumper pin from JP4 to sort this DAC A and ADC into. So, whatever DAC output I am getting, I will get it in ADC. Now, how to check this, whether I am able to read this ADC or not, how we can check? So, we can use another DAC value, another DAC which is DAC B. So, if I able to read in ADC, if I am able to read this ADC, then I can see the output in DAC B. So, confirm that here we do not need any gain converter, because here it is already analog is converted to digital form. So, it will be digital form. So, I am building it up. So, DAC B is pin number 70. See, we are able to read this DAC B. I have connected across DAC B, so we are able to read this DAC here. Similarly, you can see this. The signal sine wave what we are given from DAC we are getting here. See, maximum value is 2, minimum value is 0, and the frequency is 50 Hz. So we are able to read this sine wave from we are reading now this from DAC B. So first, so that means that my ADC is able to read the analog input, and then that has been that has given to DAC B. So this is the one utilized, and this is the external input. If we give from external, if you use any signal from external, we cannot give direct. Here I have in software I have directly added 1, but in case of external ADC pin, we cannot use like we cannot give constant 1. So we need to give use this circuit to get to add 1.5 volt DC voltage, and then we'll get the output completely in positive waveform, positive side. So here you can see first circuit is in summer, and then which will be inverter form. So to convert into non-inverting again, we use another inverting amplifier to convert into normal signal, what we expected. So now from here I am ending this session. Anyone having any doubts or questions? From here I can't see. Any questions from participants? Hello? Yeah, hello?
good morning. Hello, hello. Huh? इसी रहना है तो Good morning all. Online participants, can you hear me? We are at the last session of this 5-day GIAN course on PV fuel cell microgrid, a sustainable energy solution, PVFCMGSES-2024. So, as already I have mentioned, today we will show the demonstration of this battery supercapacitor based hybrid energy storage system, its control implementation for a DC microgrid. Okay. What? Huh. So, then the screen has to be proper, na? So, here I am going to talk about the various topologies of this hybrid energy storage system, its power management and control classification, the architecture which we are going to implement for this DC microgrid, its simulation and the experimental validation will be explained by the laboratory setup in real time will be explained by my PhD student Rasmiranjan Swai after I cover all this part. So, coming to the various topologies that is available for this hybrid energy storage system, which I skipped during explaining the power management. So, here if you will see, it is a passive topology, semi-active topology and active topology, and but while explaining about the power management, I told we are taking the active topology, but in literature you will find different topologies and its pros and cons. So, if you will see the passive topology, which is shown in this figure A and B, here the battery and supercapacitor, this hybrid storage unit is directly connected to the DC bus is one topology, and another is both battery and supercapacitor are connected parallelly and it is interfaced through another DC-DC converter and connected to the DC bus, which is supplying to the load. So, in this passive connection, okay, this connection means this topology is very simple, less costly because we are not having any control over here, but the main problem with this is the battery supercapacitor current as well as the DC bus voltage we cannot regulate. We cannot maintain this DC bus voltage constant, as well as we cannot have a charge discharge means controlled charge discharging of this hybrid energy storage system. Then coming to the second topology of this passive connection, here this hybrid energy storage system, this battery and supercapacitor should be means as both the cases we are connecting it parallelly. So, they should have same voltage level, and they once they are connected in parallel, they are connected to the through the DC bus via this DC-DC bidirectional converter. So, one advantage is here we can have we can regulate the DC bus voltage, whereas as they are connected here the regulation of individual units battery and supercapacitor we cannot control it properly, means that is the disadvantage of this topology. Then coming to this semi-active topology, here I have shown you can see here this battery and supercapacitor, one either of the storage is connected through the DC-DC converter, either means either battery is connected to the bus through a DC-DC converter, supercapacitor is interfaced directly, and it is the reverse way, battery is connected directly and supercapacitor is through this DC-DC converter. So, again what is the drawback of this system? It is means little complex than the previous one, little more costly, but the problem is the one which is connected directly we have it is not regulated. We are regulating the DC bus voltage, we are regulating the battery current if it is connected through the DC bus, and it is the other way around. Here if battery is connected directly, battery charge discharge control cannot be regulated. So, these are the problem with this passive and semi-active topology. So, we are going for the active topology. Okay. If we are there are several topologies available in literature, but if you already you have seen the architecture of PV HESS based system, wind HESS based system, we are going for this active connection, okay, where both battery and supercapacitor are connected to the DC bus through this bidirectional DC-DC converter. Okay. So, here it is. So, that means we have a better control here, both charging discharging current of the battery as well as supercapacitor can be controlled in a better way. So, and the DC bus can be regulated in a very efficient manner. Okay. So, overall efficiency of the hybrid energy storage system increases. Apart from this, so we are in this our implementation, which will be explained by Rashmi after 2-3 minutes. So, this will be means he will show this connection in detail. He will explain you the corresponding sensors, how it will be developed, how it is already been developed and already it has been implemented in real time. Before that, just I want to show other topologies, which is here instead of this battery supercapacitor, one is connected through the DC-DC converter. If you see this G and F and G, okay, and then overally after controlling the DC bus again it is connected to the load through another DC-DC converter. So, DC bus voltage regulation as well as one of the storage unit is controlled properly. Okay. And another is the one which is having a multi input single output system. Here this is the battery and supercapacitor are connected because two inputs are connected through this DC-DC converter, this MISO system you can say, and here the this is the advanced one which we have not worked with. So, this is what it is means the main thing is compared to the this active topology having two bidirectional converters, this is a single converter, but its implementation is complex. So, that is the main part of it. So, now coming to this is about the topology. Then, so if you compare this is you can see here the already what I have explained cost wise, the flexibility and DC bus voltage fluctuation, this has been compared here in this table. So, you can go through this slide. Now, coming to the power management of this hybrid energy storage system. So, this is the power management system which has been means already available in the literature. Okay. So, this is we can divide it into the classical control scheme or intelligent based control scheme. Okay. This is so in the classical we have several methods, but already I explained in detail about the filtration based method. Apart from this droop control based, sliding mode control, the deadbeat control, rule based control, all these are coming under classical, and already I told this intelligent based control, this ANN fuzzy logic based control, though it is giving more efficient, but because of the computational burden it is giving some implementation complexity. Okay. So, we have not done in this part. So, I am not going to explain anything. So, here basically I am going to explain about this filtration based control and some modified scheme of the filtration, basic the conventional filtration based which I have explained in yesterday's class in detail. Okay. Then comes the this how the reference current or power of the battery or and supercapacitor based HESS system is developed or means segregated. So, here also several controls, this PI control based, robust control, gain scheduling and this nonlinear control and fuzzy logic based control, we are going for this PI control. Okay, already you have seen. So, now coming to the architecture of this bidirectional converter which is called the active topology. So, this battery as well as supercapacitor are interfaced to the DC bus through two bidirectional converters. So, this converter design also you already know. Okay. So, this is implemented. First we have designed it, simulated it. So, I will show the simulation result. Okay. Then Rashmi will explain you. So, this filtration based control yesterday I have explained in detail. We are segregating the high pass component and low pass component through a low pass filter. Okay. If you will see, the net current is subtracted from the battery reference current and we are generating the supercapacitor reference current. So, this is a conventional filtration based control. Okay. First yesterday result I have shown with this type of control for this PVFCMGSES based microgrid. Okay. Now, this control scheme is modified, okay, and we have tried to propose one another means whatever is available in literature. First we have tried that one, then we have proposed our filtration by modifying these two or merging these two. We have tried to see the overall performance of this HESS based system, and we have found that there is a performance improvement. So, that I will show with the experimental results. And this also, this control scheme, which first one with respect to the this conventional control. So, one is this modified filtration based thing. This is the battery reference error reference is added here to improve the overall functionality, means to reduce the DC bus voltage overshoot and the tracking time, all these things are improved. Okay. So, this DC bus voltage error based filtration based method, okay. And this is another, instead of this I net minus IB ref, okay, here direct the measured battery reference current is subtracted and the supercapacitor reference is generated. So, that is with a slight variation, but it is improving the control scheme, the output of the overall control scheme is improving a lot. So, now merging these two with a VDC error compensation and also the battery current error compensation, we have proposed this modified filtration based control, that is our proposed method. So, we have tried to simulate this one. So, all these 4 topologies the control schemes along with the conventional one 5, we have tried to simulate and compare. Okay. So, this is our proposed one, the overall result. So, here this is, there is no source, means renewable energy source, we have only battery and supercapacitor, where battery is supplying the main tangent part is supplied by the supercapacitor and the steady state part is supplying, battery is supplying the steady state part. So, here you will see just the transient part, everything already this type of result, the battery current, if this is the load, and only result the condition is with the increase in load and decrease in load, we have tested or simulated this system. Okay. So, this is the corresponding VDC regulation, SOC of battery and SC are shown here and corresponding currents. Okay. So, all the reference current, the actual currents are tracking its reference value, fine. So, this is the for the proposed method, and then only this VDC, for this VDC the DC bus voltage, here we have tried to compare for all these topologies. Okay. So, how this gradual, this is the conventional one, okay, and then all those 4 control methods. How the means, if you see the undershoot and overshoot, it is gradually decreasing. If you see, this is the overshoot case and this is the undershoot case. Okay. For during the load change, transient operation, how the performance is improving, that is compared here. Okay. If you see the settling time for the load increase, load decrease, and overall undershoot and overshoot for the proposed one is so less if you will compare with the conventional one. And then this paper is also we have published in already Journal of Power Sources, you can refer this is given in this reference also. Okay. So, that you can, because of time shortage I am going little fast. So, that because actual implementation he will show you, Rashmi will show you. So, this is about the simulation result. Then I think experimental validation now you can take up, it is over to you. Okay.
Thank you very much, madam, for the introduction. Good morning all. Now, I am going to explain the experimental validation of the overall HESS system. Here we are taking for experiment, we are taking battery pack of 12 volt lead acid of 42 ampere hour of each, resulting 24 volt and 42 ampere hour. And here the inductor is taken as 0.05 and other parameters you can see, and the switching frequency here is taken as 10 kilohertz, and the load around 4.6 ohm and 2.3 ohm. And this is the overall system architecture or the connection diagram of the system, you can see here. And here we are for the measurement purpose we are taking current sensor and voltage sensor. The current sensor, the product serial number of the product name of the current sensor is LEM LA55P, which has a maximum current measurement up to 50 ampere, and here we are measuring only maximum current of 10 ampere, and the 10 ampere is converted into plus or minus 5 volt, and as it is a current sensor, we need a turns to turn ratio. So, for the turn ratio calculation, we are taking we are using this formula. Number of turn is less than equal to the maximum rating of the sensor divided by how much current we need to measure. Here in this case, we are using maximum rating is 50 ampere, and we are taking 10 ampere. To calculating this output current of the sensor, it will be become 0.05 ampere, and this sensor has also 1:1000 conversion ratio. For the number of 5 number of turn, we have I max of 10 ampere. So, output current will be become 0.05 ampere. So, input current of 10 ampere, the output measuring resistance which we are seeing here ROI, that is connected to the ground, and the output voltage, the output point. So, here the resistance output resistance will be around 100 ohm. So, some important point to taken care of while using this sensor. The output resistors should not be selected beyond 150 ohm to avoid non-linearity in the measurement reading, and to increase the accuracy in the measurement, reduce the effect of temperature changing, the maximum power dissipation should be around half watt or 1 watt. So, we are using LEM LV25P Hall effect voltage sensor for the voltage measurement purpose. Here is also the maximum maximum voltage can be measured here at the range of 10 to 500 volt, and it operated at plus or minus 5 volt 15 volt supply power supply. The manufacturer data sheet provided that the primary current of this sensor is 10 milliampere, and this sensor has 2500 is to 1000 conversion ratio. So, here is also we are selecting the output sensor and the output resistance and input resistance connected to the system. So, here are the relation, so that we calculate and the maximum power dissipated at this sensor module is around 2 watt. So, here is also some points to be noted. The output resistor should not exceed should not be selected beyond 300 ohm to avoid the non-linearity, and to increase the accuracy. So, here is also we consider the maximum power dissipated here as 1 watt or half watt or 1 watt maximum. So, now coming to the controller part. Controller for this implementation, we are using DSpace DS1103 digital controller board, which has you can see the which has some two processor such as master PPC and slave DSP 4240 F240 processor, these two separate controller. So, it will use it to generate the control signal for the switches. To control this software, to control this board, we have a software named Control Desk, which is integrated with MATLAB and RTI library, where you can see later in the next slides. This is the overview of the image of the controller. You can all the channels and the output input port are displayed or marked on the screen. The first and the number marked with 1 is ADC channels, which is from and the number marked in second, the second box maintains the DAC channel. Next two connectors are slave ADC channel and digital IO input output channel. The fifth one is the slave input IO output channel, and seventh is the CAN connector, and so on. This is the digital the master PPC. This is the layout of the master PPC or the master controller. Here we have some this is generated from the MATLAB library. We can see by typing RTI, and it will display the available ports and connectors with this with this board. And in the right side figure that depicts the connect of the pin available with the master PPC controller. Here you can see the serial numbers of the pins and the port associated with this system. The input output resources of this board are split between two processors on the board, the master PPC as I said and the slave DSP F240. By clicking on either of, you will have access to blocks that can be placed on your model that provided input output functionality associated with the respective processor. I was talking about this this library. Similarly, for the slave DSP, this is the connector of pins and this is the blocks available for the MATLAB integration. And before going to MATLAB the simulation or hardware implementation, these are the steps we have to follow to configure our hardware environment or the software environment. Now we are coming to MATLAB to follow these steps. If I type RTI, it will display the boards available with the system as I display. Here you can see two controller board or individual processor is available, master PPC and slave DSP for F240. If we double click on master PPC, the available blocks will be displayed here, and similarly the slave DSP also, these are the display available, these are the library available to integrate with the MATLAB. To run the environment, first we have to set up this system by clicking new simulation model. After creating new model, we have to configure the parameters as mentioned in the slides. First we have to save the model and set the stop time to infinite. First we have to go to the model configuration parameter. Here we have to set the stop time to infinite. Then open and edit configuration. These are that I have already opened. Set the solver parameter to OD1 Euler. Here OD1 Euler is selected. Then go to all parameter. Fixed step size should be multiple of sample time. So whatever sample time we took, then that will be multiple of the step size. It should be checked. Suppose I am taking 0.001. And third step is uncheck the optimization. Here we have to search for the parameters. Then the hardware configuration settings is displayed here. The system target file should be, by default it was grt.tlc here, grt.tlc, but for our system we have to select our this rti1103.tlc, which is this space target file. And some other parameters we have to select. For optimization, block reduction optimization, by default it was on, then we have to keep it off. Go to all parameters, search for block reduction. Block reduction, by default it is on, we have to turn it off, apply. Then signal storage reuse, we have to turn it off also. Signal storage reuse here, we have to turn it off also. Then conditional input branch execution. Conditional input branch execution, turn that off also. And the system target file, we already set this to rti1103.tlc. And after setting this system other parameters, we have to create our model. So to save time, I have already created this model. Let's go through this model. This is the model. First we have to input the import the measurements we have taken from the system. Now I am going to show the various input sensors associated with the system. This is the controller board RTI DSpace RTI1103, and the control signals are generated, and the whatever I showed, the master slave ADC or the digital IO or the slave DAC, that ports are connected and the input are given there. Also the output is taken from the those ports, and this is the battery model. Each one is having 12 volt and 42 ampere hour, So combined we are getting 24 volt and 42 ampere hour. And this is the supercapacitor we are using, which have rating of 58 farad, and each series have voltage rating of 16.2. Though combined it is getting 32.4 volt and 50 farad. This is the sensor module, the current sensor module, and this is the sensor module for supercapacitor, and this is the voltage sensor or the voltage sensor module for the VDC or load. This is the LV25 voltage sensor, and this is the LEM25 current sensor. And these are the converters associated with the system. The right side of the green light blinking in the converter, that was representing the supercapacitor module, buck boost converter for supercapacitor, and the red one is associated for the battery. Now let us coming to the modeling. The model we are taking here. Let me zoom. Here we are taking the voltage measurement from the voltage sensor through ADC channel of, if you double click on that channel, it will show the channel number. So here we are taking from channel number 19. So channel number 19 will provide the input for the voltage sensor from the voltage sensor and provide it to the controller. And here we are taking 48 voltage as voltage reference or VDC ref. We are giving that to filter out the noise, we are using this transfer function, and this is the sensor gain. For the sensor we are getting voltage gain of for the controller we are getting 10 voltage rating voltage gain of 10, or the gain of 10 from the controller board. If we provide 10 plus or minus 10 volt, the controller will scale it down to -1 or +1 volt. So we are getting around 10 of gain of 10. Similarly, the sensor also has some gain. So if we multiply, so sensor has gain of 40, and this controller has gain of 10. So if we combine those gain, we are getting 400. So the input signal is passing through the transfer function to filter the noise, and the gain is added to get the actual system voltage. So these voltage are compared here, and the error is fed to the voltage controller. Voltage controller block has a PI controller, which has the proportional or integral value which are tuned separately, and the output of this voltage controller block will be the total reference current for the HESS. So now the HESS is now the output of this voltage controller is given to the HESS system. So now it contains both the combined output or the combined current reference, which will again fed to the filter. So madam has already explained the filtration based control. So the filter is presented here. It will separate the high frequency component and the low frequency component of the system. The high frequency component of the the reference current will be the reference current for the supercapacitor, and the low frequency current, the low frequency parameter of the is the reference current for battery. So that is done here, and the output is going through the filter, first order filter, and the output of this filter will be I battery reference or battery current reference. And if we if we subtract the this reference current from the total reference, then we will get the reference current for the supercapacitor. That is done. Similar thing is done here. Now we are getting the battery reference current, and here this block subtract this battery reference current from the total reference current. Now this we get two reference current for battery and another one for supercapacitor, ISC rep, and I battery rep and ISC rep. Then I battery rep is compared to the I battery actual or actual battery current, which is also imported through the here I battery actual. It is imported from the measurement by using ADC channel of channel number 18. So, here is also we are using the transfer function to filter the noise, and here is the sensor gain. So, after that we are getting actual battery current. The actual battery current is again compared to the reference current, and the error is fed to the another controller block, that is PI, that is also PI controller, and that output of the controller block will be the duty ratio for the battery. Similarly, with the supercapacitor also we are getting reference current for the supercapacitor ISC reference, and it is again compared to the actual supercapacitor current, which is imported from the using ADC channel of 14. This is a master multiplexed converter. So, it has 4 channel inbuilt merged together, and the converter number 4 will provide 4 individual channel. So, from that we are taking only one channel, the first channel we are taking. So, it will be channel number 13. So, again it is filter noise is filtered by this transfer function, and the gain is added. So, after that we are getting actual supercapacitor reference current, that is compared with the generated reference current of supercapacitor. So, both error will be fed to the supercapacitor controller, which is also a PI controller, and the error of the output of the controller block will be the duty cycle for the supercapacitor converter, that was I explained previously. So, now we are getting 2 different duty cycle. So, we have to forward those duty cycle, or the convert the duty cycle into PWM pulse, so that our converter will run. So, to give the output from the system, we are using this also, they also provide the output DAC channel. We are using this PWM here to import the signal from the measurement port. We are using master slave master ports. Here we are using DSP 3-phase PWM generation, it is a slave port, and here we are giving the frequency as 10 kilohertz, and it has a 3-phase PWM three-phase PWM port. For the 2 ports we are giving duty cycle for one for battery and another for supercapacitor, and the third port will remain open. So, these are the rest 2 blocks are using for, here we get the I battery current, and these 2 blocks are used to retrieve the SOC of the battery and for supercapacitor. After so now the model is generated. So, after modeling the model has generated, we have to build it. So, this is the build option. So, after I click this build option, the MATLAB will generate the MATLAB has started the building process. The code will be automatically generated. So, you have to wait till then. Now, the build process has completed successfully. So, the build process has generated some file with SDF name, SDF extension. So, the SDF file will contain all the necessary code parameter or the blocks that will we use with the controller board. And the controller and this SDF file will be stored in the MATLAB home directory or the folder, home folder, root folder. Here you can see the untitled.sdf folder. So, in control desk, So, to control to use the associated after building a model, you have to control the board using the software provided which is DSpace Control Dex 5.6 of 5.6 version. In this control dex, first we have to create new project plus experiment and giving it a name. I am giving the project as and we have to also choose the root directory. And after the choosing giving the name and root directory, it is asking for the experiment name. Suppose I am leaving it by default, and here we have to choose the platform. Platform is already chosen 1103, and after choosing this, we have to choose the HDF file. HDF file is located at the root directory of the MATLAB. So, you have to browse the file from there. And after selecting this file, you have to finish. Have to click the finish. Now the new environment has created. So, it is initially it was blank. So, we have to import all the variables available with that model. For that, we have to go to this all variable description, then model root, then we have to expand it further. Here we are getting this iLoad. Here first we have to import the battery voltage. Click after selecting battery voltage, in this variable bar it is option is showing. So, click on this bar and try to drag it up to the blank screen above. If we leave the cursor, these are the options available at the time. So, first we have to use the time plotter to display the plot the values. And also we have to see the value in the real time. So, again click it and drag it and drop here, the display option will be available. So, click the display. Similarly, you can do this for other parameters also. This is VSC means supercapacitor voltage. Click drag in and drop it in the time plotter to plot the variable, and also to display it, again drag and drop and open the display. Similarly, for DC ref, the DC reference or VDC reference voltage, drag it here and drag it here. Here I am taking V battery voltage, supercapacitor voltage and VDC reference, VDC actual, SOC of battery and supercapacitor, then total reference current. Then battery reference current, then supercapacitor reference current, then the actual currents available. So, after adding this variable, we have to save the model, save project, and some other settings we have to do. First go to properties, then instruments, and to save the recording we have to add and go to recording, then create new record and double click on that, open properties, and we have to change the format of the recording. Give it the name prefix, so if it will sequentially added or renamed automatically by recording underscore here, and also turn on automatic export. the export file format should be in MATLAB file or .mat here. So, for future use it will be, the data will be stored in .mat file, and we can use it to plot or analysis for future analysis. Then we have to save the project again and click on go online. Now we can see the reading from the sensors. Here we have a battery voltage of 23.8 volt and battery SOC around 78%, and here supercapacitor and VDC reference voltage at 48 volt. And after that click on start measuring. That time plot will show the the real time reading from the sensors. Now we can turn on the switch of the controllers. Now we can see the VDC is tracking. You can focus there at around 47.3 volt. So the time plot is now recording the, or after that we will have to click the recording by clicking on start immediate. So it will start the recording. If I try to change the load, then now the controller also able to track the voltage. Here battery current, a total reference current is generated as here you can see the battery is getting discharged and time plot is recording. And after completion of the experiment, then we have to click the stop recording option. And after that stop measuring and go offline. By clicking on go offline, the pulse generation will be stopped. So the file is saved here. here you get experiment data in mat format. You can import it to the variable, and you can try to plot here. The one demerit of this system is the data is stored, if we are adding it sequentially, but the data is stored randomly. So, we have to find it which data it was. Now, the data is exported to the system, and if I try to display by using this code, now see here this data is saved, and we can plot it by using MATLAB command. See, there are two variables are stored, but problem is you have to find the which data it was. So, by identifying our system, we can easily do that. These are already explained. So, we have to save the file name and exported the automatic export, and the file data type should be in math format, so that we can use it in for future analysis. Here you can see. Now, this is the result I already previously taken. Here the result you can see the initially, and the orange one depicts the battery power, and the blue one is the PV load power, and the yellow one is the supercapacitor power. Here the load is initially it was around 180 watt, and the battery is able to provide it completely, and at the stage sorry, the load is at around 200 watt, and at 15 seconds the load is increased to 300 watt. Now, we can see the battery power is getting providing the steady state component, and the supercapacitor is getting a spike at this 15 seconds. So, this will represent the transient, and it is handled by the supercapacitor. Now, the right side plot is depicting the current output of the system. Similarly, the orange one is the reference supercapacitor reference current, and orange and black are both representing battery current, and blue one is the load current. Here you can see the battery is trying to provide the steady state power, which is in almost constant form, and there is a spike also present in the at 15 seconds and 25 seconds, because at 25 seconds the load is reduced to again 200 watt, which is clearly visible in this graph. And this is the voltage DC bus voltage tracking using experimental method, and all other methods are filtration, all the other control methods are compared here. So, we can see here the red one is the fast small axis is the actual the proposed control method. Here you can see the smoothing of the transient, and the undershoot of the system is also very low. Here also you can see other different available control strategy we have already tested. Now, these are the references. Thank you. If any question? Okay.